cutting through the hype, quantum and AI technology. So let's welcome on stage Kalev Kaarna from Metrosert, Johannes Heinsoo from IQM, Roland from Oxford Ionics, and Joosep from NICPB. Stage yours.
Thank you, guys, for coming. Maybe a few things I wanted to highlight about the awesome panel what we have. That Johannes comes from IQM, which recently raised 275 million in a B round. Roland comes from, he's a senior quantum architect at Oxford Ionics, which was last year in June acquired for 1 billion by IonQ. And last but not least, from our own Estonian research institution, Kalev in Estonia, Joosep. So let me start with quantum, especially quantum computing. There's lots of misconceptions and misunderstandings. Johannes, what is one myth or misunderstanding what you would like to bust in quantum computing?
Okay, since I get to go first, I get to pick the easiest. One thing people often misunderstand is that perhaps quantum computers just do everything faster. They just maybe will accelerate everything, and that's not true. They only accelerate certain algorithms which can make use of these quantum features, so the subset, and they actually have 3 orders of magnitude slower clock rate than normal computers. But in the end, they will make up for it because of the exponential advantage at executing these algorithms. So even if they are 3 orders of magnitude slower and maybe 3 orders of magnitude more expensive, it's going to be worth it.
Mm-hmm. Roland, any myths you want to bust?
Yes, so people miss the point that the important applications are most likely first going to come from chemistry, from material science, and people forget about how much resources mankind spends wasting time on the slow processes of developing chemistry and medicine. And then the other one, which is that we're not immediately going to be able to read your mind. Mm-hmm. We can't just unlock the brain by simulating a quantum system, and maybe that's something which people hope we could immediately do, but not yet.
I'm not a physicist, but dealing at Metrosert also with quantum topics, I have also been in situations where I had to explain what's the difference between like supercomputer and quantum computer. And as not being a physicist, I can cut corners. So the metaphor which helped me to understand the difference is that let's assume that it's not technically correct, but let's assume that if we talk in a quantum computer, we have very small particles which help to do the calculations, that for these particles, time doesn't matter. That if I have 10 ways how to get from home to work, the particle knows which out of these 10 is the most efficient way how to get to work. Now the problem is that I can't give me the right answer, that I can sample one of the possible answers, and by coding I can increase the probability that I sample the right answer. So that it's the game of probabilities that can I get the right answer from a quantum computer? Joosep, am I totally wrong, or would this probabilities and sampling and getting the right answer from quantum computer, would it make sense, or do you have a better metaphor how to explain to people what's the difference between supercomputer and quantum computer?
Right, so supercomputing is a technology that has developed for, 60, 70 years, improving exponentially. We are all familiar with Moore's law. Every, 2.5 years, we double the computing power of chips. Whereas quantum computing, it's, as far as I see, we're really in the initial phases now where we're still figuring out what is the transistor. Mm-hmm. So the transistor of the supercomputer has been shrinking for 70 years, and it's basically like a fine-tuned technology now that's already in production. Whereas for quantum computing, we are still in the exploratory phase. how should we build this technology, and then how to scale it up. That phase is still coming. Now, how does it work? And that's a whole different topic. But I would say, kind of echoing what Johannes and Roland said earlier, is that it makes sense to think about quantum computing if, first of all, you have some kind of a computing problem. So you have some data, you have some questions that you are trying to answer with the data, and ideally your problem should deal with quantum phenomena. So if you are doing some kind of manufacturing of wood products, most likely quantum computing is not your first toolkit or first tool in your toolkit. But if you are manufacturing new medicines, new drugs, or perhaps you're studying particles like I do at CERN, then which are fundamentally quantum objects, then quantum computing would be a tool that could maybe in 5 to 10 years be something that you should think about.
Johannes, with that line, you shared to me an article where the state of quantum computing was compared to a hot air balloon, that it's super difficult to get up and it's super difficult to control, but it's the only technology which will allow us to explore new places in the map, that we can detect on particle level stuff which we couldn't with a theory or with traditional testings. What do you see that where the quantum is right now? That what we heard from Joosep, some of the applications where stuff can happen and for whom it is useful. What's your take for whom the quantum is right now useful, and when it would become useful for more traditional applications?
Yeah. I could also come back to the title of the panel, right? Is it a hype or is it actually useful? And I think you're cutting to the heart of it. It's like it's one of these misconceptions, or a confusion, because in the public, in outreach and so on, and in popular science, there's a lot of statements which are sometimes outdated. Sometimes they say that the quantum computers are super small and they are, or maybe they are never going to be useful. They already do correct calculations, just they already simulate molecules in a correct way, just the molecules which fit to the quantum memory today are too small. But too small for industrial application, and then these people are right who say that maybe these industrial applications are still maybe 5, maybe 30 years away. They could be right, but what people don't understand, who don't follow this technology closely, is that already for a few years we are definitely in the era where quantum computers can do some calculations. Maybe they are not useful, but they can do some calculations which normal computers cannot do. And we are also definitely in an era where we now have a lot of really high-profile academic scientific research done using quantum computers, not about quantum computers. And these areas, so these are these scientific areas which exactly also Joosep mentioned, which relate to something else which is already quantum. And today the most accessible, or the one which is going to be impacted first, is solid-state theory and high-energy physics, some like particles which live in the lattice and have quantum phenomena, and if you need to understand them. And so today science is already happening, and it is already possible. I think it has happened before, but sometimes science does something which does not have immediate application, and suddenly somebody finds a value for this new science being done. So it is possible that some industrial value, I think, from these computations could come in an unexpected way immediately. But this is definitely a fact that if we pour enough money into it and we can scale the quantum computers to millions of qubits, quantum bits, there will be a guaranteed industrial advantage. The only question is now, will it happen immediately by some surprise? Will it take 5 years? Or in a pessimistic take, maybe it's going to take 30 years. But the first applications are likely some material science or chemistry problems. And this is definitely not something which is not important. It is super important because material science is absolutely everywhere in our commodity products. Like we already, I think every quantum technology company, including mine and Roland's, already has collaborations with, for example, car manufacturers who want to understand why do batteries age so fast. They already have quantum chemistry problems inside, and suddenly we could make, if we would solve them, maybe with help of quantum computers, maybe with the help of AI. There's a competition between AI and quantum because we are addressing maybe the similar problems. But this sort of technology might enable a success which might enable very reliable batteries or very cheap fertilizers or oxygen production for space travel. It will have secondary consequences which will change our world, and that's guaranteed. The only question is when.
So IQM prediction is 5 to 30 years. Oxford Ionics, you have different technology which can use off-the-shelf parts for electronics and so forth. Roland, what's your prediction?
You really have to define a question like what are you looking for, because we are already in an area where we can do stuff which normal computers cannot. And now are you asking for scientific advantage, scientific utility, whatever that means, or are you asking for like industrial quantum advantage such that a company which pours money into would get returns? You have to define which one you...
That's a good point, that we like research advantage, business advantage, meaning that I can get something faster. That basically supercomputers can do it also, but I can get something faster, and the quantum advantage that I can get something which you can't do with a supercomputer and which has value to business in business sense. Thank you for pointing this out, that these 3 layers. So, Roland,
Yes,
what's your
exactly.
case? Where are we?
So if I just summarize, basically several companies and research groups even have shown quantum supremacy. Yeah, they can do computation that is not tractable on a classical computer. It's so complicated it would take, maybe the age of the universe, maybe a bit less, but a very long time. These are demo experiments. They are not useful because they have been artificially generated to be really hard on classical hardware. There's quantum utility, which is what we are chasing. Yeah, this means that the cost of doing the calculation on a quantum device gives us a meaningful win in terms of the resources that we use, such that it's economically viable. We are getting close to it. Our company, IonQ, we have some elegant examples of, for example, improving the meshing in multiphysics simulations, where we have shown an advantage compared to existing classical algorithms, and so on, but these are the advantage. So the advantage will only turn into profit if it's adopted. This adoption will only happen if the advantage is approximately 10 times or more than the current status quo. Yeah. Otherwise, companies say, hey, the business risk is too big. Yes, you give me 10% improvement, but it's super risky, it's really expensive, I don't want to do it. So we have to bridge that gap. We have to get another factors of few to bring down the power of quantum. The price is already low. The price per qubit of the quantum systems is really quite reasonable for most platforms. It's really nice for trapped ions, if I may say, which is the platform that I'm working with. So that's all good, but these systems have to become larger, more powerful, and that's what we're working on very hard. As you ask, everybody can go online, check out our roadmap. We're confident that we're going to see a few hundred qubit devices coming up at the end of this year, next year. After that, 10,000 up to 1 million qubits before the end of this decade, so before 2030.
Joosep, before the stage, you had a radical idea that companies should not actually focus so much on quantum before these tens of thousands or millions of qubits are available, but they should focus on high-powered computation that use that, because in most cases you have hybrid model that 90% of the computation is done by hyper-powered computer and 10% is done by quantum. So if you don't know how to use a supercomputer, it's pretty unlikely that you can get something out of this. And also that the second question on top of it, that can you explain what is quantum-enabled AI?
Right, so 2 questions, both of them big ones. So if I start with the first one, just coming back to my original point, we're not going to have a quantum laptop, quantum desktop in our office corner where we put our wood panel optimization, to run better than on a normal laptop. So you have to have a business that is data intensive, that has hard computational problems. And today, when you have such problems, most likely you will solve them either on the cloud or in certain cases, you will solve them on supercomputers, which are essentially like national infrastructure. So in the US, there are the supercomputers in the national labs, and in Europe, there are let's say, connected to universities, but also available for businesses. And the availability already today of quantum devices produced by, for example, Johannes' company is through these supercomputing centers. So you essentially connect via an API, you run your jobs on someone else's machine somewhere else. Thankfully, I think most businesses already know how to do this. Using cloud is not a very, very strange phenomenon, but you have to be in this phase of operation where you are used to doing that, you are used to sending your problems somewhere else. And I think if I think with kind of the quick pace of adoption of AI, so maybe 5-10 years ago, if I was here on the stage or somewhere in this conference talking about language models, people would think I'm crazy, I'm some kind of dusty academic that does something completely irrelevant, right? But today you go and chat with a GPU or with maybe 10,000 GPUs, and somehow you find that it provides you business value, right? So I believe with the quantum systems, it could come somehow in a similar way, that these systems are available somewhere, they are plugged into some kind of, I don't know, not chatbot, but something that you're using, and then, you don't have to own it. You don't have to own 10,000 GPUs to derive value from AI. Similarly, you don't have to own the quantum computer to derive value from it, but you have to know what to do with it, and you have to have the problems that are relevant for it. I think this is also the case for AI. You put in some random stuff, I mean, you get something out that looks like an answer, but whether it's useful or not, you don't know. And now quantum-enabled AI, so yeah, AI has as well a long history of development. It's essentially mathematical optimization on data, right? You have a specific question, you have some data, you optimize your model, which is some kind of, essentially like artificial neural network. And ideally, it gives you answers that look like correct answers. And ideally, they are also useful for you. So now we have very quickly kind of scaled up these AI systems. And it turns out that one very specific approach, which is this language model where you just generate words based on previous words, it's very cool. You can do lots of cool things with it, right? But this is like, how do I say? It's like really scaling up one very specific branch of the whole set of technologies that is AI. So in a more wider sense, certain types of problems that you might want to solve with machine learning or AI, they might map well to quantum systems. So if you have very little data, or if your kind of correlations in the data are complicated or produced by quantum systems, then ideally, if you don't have to take a quantum system, make it classical, then solve it using classical computing and then somehow interpret it, if you can just keep it all in quantum, then you have the advantage. But I think today, if I had 99.9% of problems, quantum machine learning is not the first tool that you should be looking for. I think it's only if you have very specific kind of problems dealing with quantum systems at the initial stage.
Yes.
Maybe just to add a comment. To me, a good way to think about it is, like we think about modern compute, is that inside the computer or a data center we have CPUs and GPUs, different types of processors which are good at different types of tasks. Now, very soon, we're going to have QPUs, so quantum processing units. And now, the compute infrastructure will decide exactly this part of the problem can be handled by the GPU, this CPU, this QPU, and it would chop the problem up and go. And typically, a user wouldn't hopefully even know that that part of the problem is being sent to a quantum computer. It can be hidden away from the high-level user, for sure, of course. Right now, we're mostly seeing academic users who actually want to see the low-level access. In the future, that will not be the main use case. That will be for exploration and science, and really using it. It's going to be a black box device that's really good at doing something that the other black boxes, because no one of us understands how GPUs or CPUs work, can do. We still use them.
But this is also the opportunity, because if it's today not a black box because it's still under development, which means that still there's an opportunity to join. Like it's a new area of computation, and we have tried to invent few programming languages, but I think there's already a paradigm shift, which means that all the programming languages you see around there for quantum computers, I think they are already useless. It's already known. Like once we switch on error correction, quantum error correction, it's going to change the modality or the approach. So I think we need new programming languages, and how you do quantum computation it still needs to be, in some sense, invented. Like there's these high-level applications which we expect, and we have like educated guess that it's going to be true that with quantum chemistry, AI-assisted materials research, like drug discovery, using quantum-enabled AI, like this will happen. And then we are working on these quantum transistors, like me and Roland, this is our day job. And in between, in a stack, there's this hole. This hole needs to be filled. And so this is an opportunity, like if you still are choosing like what to study in your career or where to pivot from, it's a bit of hard work to learn, but there's an opportunity to fill this stack, and it's a very, very exciting time for to be in this industry. Like Joosep is approaching from the high-performance computing side, and we are approaching with Roland from the hardware side. Somewhere in the middle we will meet, and it's exciting because we get to fill this black uncovered spot.
It's very good that we got the opportunities. It's a startup day, so a bunch of potential founders and entrepreneurs here. Johannes, you actually had very good two examples, one about the opportunities, one about cables, and the other about the cooperation with a client, with a VTT, how it ended up with actual spin-out. Could you explain that? Where's the opportunity in cables regarding the quantum computers?
So one short step back, why did we even come to this topic was, physicists, I think, the majority are convinced that quantum computing is possible. There are few skeptics, but majority, it's settled because we have shown all of these small things to work and scale. And now, so building a big industrially useful quantum computer is no longer a physics problem. I'm a physicist, but I'm a minority in the company. Most of my colleagues around me are engineers, computer science engineers, mechanical engineers, electronical engineers, material scientists. And we really need them, we need more of them, because this vertical stack, has so many different hard engineering problems which need to be solved. It's not a physics problem anymore. So, and then this as a ridiculous but actually a really reasonable example is that we need better microwave connectors. Our next generation quantum computer will have 1,000 qubits. It will require 4,000 coaxial cables which are connected to the processor, and it's not feasible if everyone has like a connector with a nut you need to turn. So they really need to be miniaturized, and this is really like electrical engineering problem. There's a little bit of material science because these connectors, they need to work at very, very cold temperatures, at millikelvin temperatures, 6 orders of magnitude cooler than your body. So it's hard engineering, but it's in some sense like electrical engineering. You don't need any quantum mechanics to solve that problem. And as an example how these sort of problems have already been solved outside of our company. Our first client for our company was a National Research Center in Finland, VTT, which bought with a national tender a set of computers from us with different sizes. And one part of our stack was missing because usually academic labs would get a very special amplifier from USA. But the USA didn't want to export them anymore because it's like WS technology, very, very, very sensitive quantum-limited amplifier, which can also be used to listen to the normal mobile phone signal from the space. So very sensitive amplifiers. We needed such amplifiers, and the usual source was from MIT, from USA. So in VTT, researchers started making them, and now they have a spin-off company. They are part of our technology stack, and they will, I think, also have many other applications. And if quantum computers will fail, these companies which make these amplifiers, they will succeed. And we need other things as well. For example, in Germany, where we deliver to a national supercomputing center, LRZ, they wanted to integrate our quantum computer into HPC software stack. There's a job workload manager called Slurm, which is very widely used as a load manager, and they wanted to use this also to manage the workload on the quantum computer, and this integration didn't exist. in Technical University of Munich, they solved that problem. They wrote this necessary HPC integration software, made a spin-off company, and this is now part of our product stack. So everywhere, I think this hardware can be like this nucleation center where local ecosystem can emerge around and solve some part of the stack.
Roland, what kind of opportunities you see for new startups to fill the gaps?
So, of course, yeah, developing hardware for these devices. There's a big gap in developing algorithms and use cases because in many cases, people who work with quantum computers know there's a way to do something. With classical algorithms, people have shown that you can always make things better, and they put a lot of resources into this. So definitely algorithm development. And one shouldn't forget that quantum technologies are not only quantum computation. So there's a wide range of technologies which are quantum technologies and that affect our everyday lives and are really accessible. So, for example, GPS-free navigation. You can effectively, what this means is that you fly your plane with a quantum gyroscope that is always on point and never goes wrong. These planes are already flying. You can have atomic clocks on satellites, on GPSs, and on ground links, making GPS more accurate. Quantum safe networks, so how to have communication which is provenly unhackable and provenly safe. So these are some examples. In general, cybersecurity is a big one where Estonia can contribute because the whole world is going through this transition right now to transfer over to a quantum secure
Post-quantum encryption.
Post-quantum encryption system to be ready when quantum computers come, such that we just couldn't easily hack into everything. And timelines are rapidly being pulled forward. People were lazy and laid back, but we're seeing now that we needed these things yesterday. So these are just only a few examples.
Yeah, regarding cyber, then it's already known that record now, crack later, that this is already happening, that Chinese and all the other players are already collecting data which they can't crack right now, but will be...
People are definitely worried about this, exactly, because we can always re-encrypt our current communication, but if someone has been recording encrypted communications, maybe, and it is likely that it will be crackable in the future.
Joosep, you come from a different angle, not from hardware side. What kind of opportunities you see for new startups?
Right, so I work more on the software side, on the machine learning and applications layer. So maybe I just summarize the stack as I saw it. Johannes talked about the hardware part, and I think there are nice opportunities there. Roland, you talked about kind of the algorithms, the software stack. And I think on top of this is sort of the application stack, which we kind of started out with asking like, where would quantum computing be useful? And I think today this is largely let's say, yeah, chemistry problems, drug design problems, which are right now still in the domain of science. But I think here Estonia also has quite a good opportunity because we have rather strong academic background, maybe too strong academic background, and
Too strong.
right.
Too strong.
That is true, yeah.
What do you mean by too strong?
Well, I mean that we don't always know how to use our brain potential,
Yeah.
right?
Okay.
So this is a topic that has been raised also by the current Academy of Sciences, for example. They have a new administration, and like how do we build high-tech industry in Estonia? And I think one part of it is, for example, pharmaceuticals, right? Making and predicting new drugs, things that you can do essentially in silico. So before you go to these medical trials, if you can speed this up using, for example, quantum computing, I think this would be something that Estonia could do rather well. And similarly, other fields where you need some kind of specialized domain knowledge, which we might already have in our academic community and business community, and then this capability to implement this in the computers. But I stress again that first you need to be able to think computationally in the first place. And this is not something that comes automatically. And now in the age of having AI do everything, it's not so clear how exactly people should think about this, I think. Like, will we just upload our Word document to ChatGPT and it tells us the answer, or will we still be able to think algorithmically, think how to break a large problem into parts, find the data that we need for different parts and write code for this? For example, now, even though GPUs have been in production for, I would say, 15, 20 years, still a GPU programmer, one who can do it at the world-class level, is somebody who commands very high market value. And for example, DeepSeek, the Chinese clone of ChatGPT, it was so good because they had such skilled GPU engineers who could make maximal use of their device. They had these poor low-end GPUs from NVIDIA. They can't use the best ones, but they were able to work at a very low level in the hardware and run this model training in a much more optimal way. So my question is if still this kind of let's say hardcore software skills will be useful, and I think there will be some use for this, then Estonia has still a good chance to play a role there as well.
I like very much what Joosep said. I think it's not so well-known fact that also first 3D computer game Doom was made by hacking GPU. It got the performance so high only because they abused some internal feature which allowed more quickly start drawing lines on the next pixels on the next line. So it reverse engineered and hacked and used some sort of hidden engineering feature which enabled squeezing a sufficient performance out of it. And if you want to make use of quantum technologies today, you have to be on that level, or hacker level, I think. That's the state today, but we don't know about the future, as Joosep said, that maybe AI will translate the problem for you into quantum computing language. I feel that there's always this diminishing returns, that last mile somewhere, this highly skilled and well-paid engineer is still necessary to squeeze the last out. But today one needs to be this sort of low-level hacker. And we need more. I think it's not too late. I think we still need these more and more of these hackers.
Which is very good change of topics. We talked about the opportunities. So what should Estonia do in order to catch the train or not be left behind? Roland, what are your ideas? How do you see that we're a small country, not too many resources, too good science in some areas? What should we do in order to catch the train of quantum tech development?
There's many ways to skin a cat, right? Don't do that. But basically, I think what has to happen is that we have to break the mindset that Estonia is a software-only country. Okay. Estonia is only something that can develop web applications for others. And realize that no, there's an amazing skill set of hardcore scientists, electrical engineers, and electronics industry. Tap into it, start building hardware on all levels. If you have people who play with hardware, rip it apart, see what's inside, they will easily say, hey, this thing can be better, I'm going to make my own company, improve this, I'm going to sell it to those big guys. You can always do that. There's plenty of room in this space. And people can enter from all kinds of levels, from all kinds of skill sets. Definitely if they come from deep skill set backgrounds, maybe from knowledge pools which are not useful anymore. Like Johannes mentioned that there's some old, was it Nokia or Ericsson employees who are extremely skilled FPGA programmers that they're tapping into.
Yeah, in
There's
North
definitely
Finland there was I think in a city called Oulu.
Yes.
There was a big Nokia office with a lot of electrical engineers. And now, if you take a Uber or a Bolt in Oulu, you might have a taxi driver who can teach you how to program FPGAs. Yeah, and we are making use of this unused labor because FPGA engineering is some very unique skill. Absolutely.
You know, I can immediately say where I'm trying to hire right now really highly skilled analog electronics engineers. And I know for a fact that some of the old school engineers from Tartu, from the Institute of Physics, would be amazing at this job. They have exactly the right intuition. They have crazy amount of experience. We just have to access this. So just start building hardware, convince the guys on the top who are capable of making big investments. This is going to require millions or tens of millions to really have a solid starting point, to start playing with hardware, and then it will just take off.
So playing with hardware, investing into creating these opportunities and using skill sets we already have. Joosep, what's your take? What we should do in Estonia in order to catch the train?
So I guess the question is which train? There are many trains running in parallel, and I think some of them we have missed already a long time ago. For example, we will never build chip-making facilities, ASML, TSMC, these kind of things, right? So now the question is, in this quantum race, what trains can we still catch, and what trains does it make sense to catch for which you don't need this same type of capital investments? Yeah, I think Roland's points were great, right? My question is sort of like how you go from this this type of hardware that people do in a garage to this type of stuff that you guys do, right? You need, first of all, this, there is some technological basis which we simply lack. For example, we have, I think, no clean rooms in Estonia, or do we have any clean room? I don't know.
Mini clean rooms.
Mini clean rooms,
Yeah.
right?
Yeah.
So clean room is a room where there is very little dust, so you can actually do this kind of very sensitive,
Manufacturing.
processes essentially, like producing chips or, I don't know what you guys actually do in the clean room. So clean
do
room,
make
I
chips.
think this kind of thing, right? This ultra low temperature know-how, which is totally non-trivial as well, right? So some things you will have to buy in, some things you need to develop in the spot, right? And what is the right angle from the hardware side? It's difficult for me to say, not being a hardware guy. So I kind of still, speak more for the software side, which is where my expertise is. That you can build a system, but if you don't know how to use the system, it's not that great, right? So coming back to the classical computing, we have NVIDIA GPUs, we have AMD GPUs, and we have Intel GPUs. Everybody knows NVIDIA, it's very easy to use. AMD, if you tried to use it 2 years ago, you would rather jump off the roof of the building than try to use it. Now it's getting better, but it takes a long time. So basically there is this huge software moat that NVIDIA has built around the product, making it very easy to use, all this backward, forward compatibility, things that are take a long time to invest in to actually yield a profit. And I think the same could be true for this quantum stuff, is that what kind of sort of software layer you build on top, how easily it is integrated with other things, how well you can manage it kind of in a whole life cycle, this will play a huge role. And I think we will not be creating this software in Estonia because we are neither IQM nor IonQ or Google or whoever are the other guys who are making the quantum computer. But at best we will be on the user side, on the application side there. So then where can you go in the stack that it's actually useful? So if you are just in the chatbot, I think it's not so useful. So you want to be in the value chain, I think, a little bit before that somewhere. These are my thoughts.
And in order to have these capabilities in Estonia to create this software on a right application layer or make the connectivity more easy, what to see? Is there anything extra we should do, or we are already educating enough people at universities?
So I'm not aware that Estonia has any kind of specific quantum, quantum-specific, I don't know, software or even hardware education. So I think Tartu has one quantum algorithm course, which is done once in a while.
I think this semester maybe is the first one where some, like this micrograd,
Micro degree,
degrees, yeah.
which is started in University of Tartu, but it's an introduction thing. But it's a start. I think Roland said that we already own some lottery tickets, and Joosep challenged if we have a correct type of lottery tickets, and I would say that let's buy some more lottery tickets, and maybe we can diversify a little bit, maybe we have some classical electrical engineering potential, maybe untapped, which Roland mentioned, but let's create and Joosep was suggesting that maybe we should have this high stack. We should bet on a higher levels of stack because it might be too late for the low-level train. But I'd say there's still time, there's like this gap in between, and even if we later not become the developers in this mid-stack and low-level, we for sure still can become like smart customers. like you can maybe do this innovation on higher level of stack if you know how lowers work. So even if we don't develop them, I think we should buy some lottery tickets which allow us to learn it. And one way to do that, like because now 5 years ago it wasn't true, but now we have many of these quantum startups who can deliver full stack systems. They have the prices come for the full system is gotten sufficiently low, so maybe even universities can afford them, like less than $1 million of upfront investment. So you can build a lab where like a S-Cube style, students can start doing projects, tinker with the system, break it, fix it, learn how to calibrate, and then they might become educated to innovate the applications or maybe replace somewhere in this hardware stack, even maybe. Like it's such a large diversity of this diversity of engineering which is necessary. So I think there's great chance to innovate inside this stack. I think it's hard to build, like Joosep said, a new train which would provide a full stack, but definitely there's innovation and valuable IP which can be created in this stack, and it has double-use applications, even if quantum computing might die for quantum computing applications, maybe because AI, for example, is so good that useful quantum computers are not needed because AI just does everything. Drug is discovered with AI without quantum, maybe this is possible. But these technologies have other applications for fundamental science, or maybe like these, as I told, these amplifiers, for example, which are very, very sensitive. They can be used for military purposes, or for example, which is like well funded these days. So these technologies have other uses as well. So maybe it's a safe bet would be to buy some lottery tickets, which would enable us to.
But what are the lottery tickets? I want to know.
Well, if I may be specific, we could buy one.
IQM device?
Yeah, we have educational offer, 1 million system, less than 1 million. It's fully documented. You own the hardware, so you can replace parts. You can, for example, make your own software which would calibrate the quantum bits. You would learn absolutely everything which is also necessary, for example, for NMR.
So I think the lottery tickets are people. It's top-level research groups. Yeah. You should try to bring in some top professor from somewhere who has a research idea that has academic potential and that has some kind of
but for example, S-Cube wasn't made this way. Like in S-Cube, there was like a super talented guy. It was my classmate who made the motherboard for the first S-Cube, right? And now they are selling these satellite motherboards to companies all over the world. So the same way, if we make just some nucleation hub where talent is motivated to stay and tinker it at home, they don't need to go to, I don't know, MIT to tinker with this sort of system. This would maybe like increase the chance that some of these bright minds grow here and stay here and invite others to be here.
So S-Cube model, which is, I think, an awesome example that we have once played this lottery and won, and why not replicate it? Bringing in high-level guys, giving them free hands, hey, build something, and pooling. It's like a magnet that if it's gravitation, it brings in other guys. So if people
want to buy a machine, they can buy a machine. If they want to build a machine, they can build a machine. So the people who know where this field is, I think, can build this ecosystem around them.
Yeah,
Roland,
and then I think now we come to the important point, which we already love, that is money. Yeah.
Yes.
People are going to say, yeah, okay, you got a smart guy who wants to buy and build a machine. No money. Yeah. We need a paradigm shift where we understand that we have enough concrete. We have already even invested enough into concrete. The best part is always in the kitchen. Mm-hmm. Yeah. We have plenty of kitchens. Stop building huge halls of cold concrete. We can save millions by directing those resources into people, mostly. That's where we need the money, and into a little bit of seed for the hardware. Mm-hmm. And suddenly these tens or hundreds of millions that get turned into building empty, cold buildings in the middle of fields, which are totally empty and have huge costs for heating them and whatnot, and other problems, suddenly are replaced with really good people who fill those spaces. They're crammed together, they're creative, they get well paid so they can have families and kids and happy lives, and then they make really good things. So I think that's another mentality shift that we need. After going from pure software to software hardware, we also need going from concrete to people. And if there's forces high above that say it's easy to fund concrete but hard to give money to people, then we need a will to say, this is not okay. We have to say, without people, everything is nothing. Yeah.
There's also one discussion about if we go to invest into, should we invest into buying a quantum computer for IQM or somebody else, where we can plug and play and do all kinds of crazy stuff, kind of a CubeSat model where we build and learn. And the other camp says that nowadays we should just buy access to the cloud options of getting to the cloud computer. So, three of you, where do you stand? Are you in a camp of let's invest into cloud, or let's invest into one physical computer we can take parts? So on IQM, I would assume that you, Johannes, you would prefer if somebody would buy the actual computer to Estonia.
I think they are all lottery types with different rewards.
Okay.
Like, and they have like different upsides, right? If you also want hardware engineers to emerge from it, I think you need to buy some hardware which people can tinker with. Today, the first panel, one of the panelists was Jaak Vilo, who also said that mentions a few upsides of relying on your hardware intellectual property, or like bringing value by unique hardware, because when you have these sort of moats which later protect you, and upfront investments are bigger, but it is also like more less competing. Like today, it's very easy to make another app, but it's much harder to copy your hardware. So if you want, if our ambition is that we want hardware engineers to emerge from Estonia, we need to buy such lottery tickets which offer this as a main prize. So I think for this you need perhaps to own the hardware such that you would be allowed to change it. But today you can already do some hardware research also with cloud platforms, because as we told, this middleware doesn't exist, then or is underdeveloped. Then multiple providers, including us, have opened up cloud access at the lower level, which allows you to do like not only computation with the quantum computer, but you can do like physics experiments. You can do sort of spectroscopy. And study really the Hamiltonian, which describes the quantum processor. You're not only limited to the gate level access, so you can already do some sort of entry
physics stuff,
and sort of education with that, and research. And one lottery ticket was buying hardware, and second one, as Joosep mentioned, is to attract some person who would be ready to teach it. And I think one reason why they don't come is that we don't have this academic job security and so on. So we really like way more generous welcome packages. So salary for somebody would be guaranteed for quite few years, like you don't need to come with your own European research grant to be decently funded in Estonia. Today there's like too low job security, and even if you are top talent in the world, these grants are like small, you cannot hire another person and so on. We could fix that to have more lottery tickets.
Joosep, cloud or physical?
Roland.
Roland.
Yes, so, okay, of course, yeah, buy all the devices, but also, more seriously, we have to find the synergies that we have. We have to find the good people that we already have and ask them, hey, what would make you, together with the other institutions, together with the facilities that we have, give us, where 1 + 1 = 30 or 3,000 or 3 million? Mm-hmm. Where do we have the big synergies? And then what are the missing elements that we can pull in? And what is the security you need? In most cases, again, we will probably find an empty space where to place people, the offices and the machinery. In some cases, we have some good people we would need to pull in, maybe try to attract them away with a carrot from another well-paying job into this field, or maybe attract them from abroad. And then, of course, they will want toys. Those toys might be access to online tools, tokens, so to say, to access the web. It might be hardware. And as I see it, the healthiest package would be to bring it all together, have a center, so to say, center of excellence, not in the old sense of the word, but have a center really of competence where the individual parties are happy to come together, combine resources, and make really cool things happen.
So it's, if we have limited money, then you would recommend that the scientist we bring in, he will decide, or she will
We have the
decide.
money in the country.
Okay.
We have to
reallocate it.
reallocate it, and we have to tap into the amazing people that we have, who have really nice bank accounts, and they're definitely happy to help if someone asks them nicely.
Joosep, cloud or physical computer?
So your question was, should you invest in cloud? I think you invest in cloud only if you're Amazon. Otherwise, you spend on cloud.
Yes, spend, sorry. Spend on cloud.
And I think this is important distinction. So unless you have a problem you need to solve with quantum, you don't need to spend on cloud credits for quantum, or you want to learn about it or so. So then the question is, like, what's your goal? Do you want to kickstart the field in Estonia? And I think for this, there are established models, essentially. Like, one does not have to invent a new kind of system. Like, it's basically what people have been talking about here on the panel. So you try to attract investment from Europe, like big grants, ERC grants or other things. You top this off with private money or with state money if it's not possible to find otherwise. So you make some kind of an attractive package, and then these people, you bring in the top brains, and they hire the local brains, and they build the systems that they think should be built. So I think just buying stuff, boxes, which you don't know what to do with it, is a short-term joy. Like, I know the joy of getting a new device and trying to plug it in and then realize the drivers, I don't know where to get the drivers. I have to contact a company or something, or firmware or something, and then it sits in your corner for the next 2 years. So I think you need the people who know what to do with these devices, and the models for this exist. The models are universities, and of course the model of university evolves. It is not that you give money to some guy or girl who's sitting in an office and doing nothing, but rather that we have to somehow also engage the private sector, so that the research groups are doing things that have also relevance to the private sector, but the state investment has still an important role for this. And state investment, the models for this also exist. It's competitive funding from either Europe or Estonia. So I think the wheel does not have to be reinvented. It's more like enough people have to be interested, and then also to be successful at this. So now the problem is the bright quantum scientists that Estonia have gone to work in these companies who make the machine, because that's the only place you can do this, is in a company that's elsewhere, right? So, how to convince these people to apply for a ERC grant, and then to bring this know-how back to Estonia, I think that is the question.
Alexander, can the audience ask also questions somehow, or how does it work?
Yes, so they can ask on Slido. We do have 2 questions already. You can also ask by raising the hand if you want.
My question is in the Slido, but I can say it later.
No, if it's in Slido, then it's okay. So I have it. So you already want to take questions?
I just wanted to check how it works, but I'll ask one round and then I'll take the audience question. So you had a very good point at how to get Estonians from abroad back. So Roland, what should happen to get you back to Estonia?
A very good question.
I think it's not only about money.
Yeah, it's definitely not about money. It's about creating a situation where there's true excitement, true belief, and a true community of people, resources, and institutions who say that we can do something good long term, something powerful long term, that we're not going to give you 2 million and then you hire 2 guys and after 3 years we say, sorry, the project ended, go away. Yeah.
So you want
it has to be
long-term security.
Everybody wants long-term job security. Everybody wants to work with good people and have a nice life. So if we can combine what we have already, then that's the magic formula.
Johannes, what should it take to get you back to Estonia?
Well, I think I can answer in a more abstract way, because I know at least some of my friends are considering coming back. Okay, so how to make the life happy for them. And I think we do need generous welcome packages, and it's not by means of like monetary compensation for the researcher or so, but it's but the money does affect the environment around them. Like, can they hire people? Do they have money for the lab or the cloud tokens? So like it's very hard to do something if you have like only research funding for like 4 years for 1.5 persons, right? And like this way, it's very hard to do anything ambitious. So and today, though, I think this funding is not sufficiently generous and secure and predictable. There's like such a very high-profile researchers are not funded in Estonia. They don't win the grants. The only way is to bring in very competitive European research money. And why, when one would bring it here, why not bring it somewhere else where I already can join somebody in a weekly seminar who do similar research? So we need to compensate for this with some other generosity, such that we would have more secured career or like near-term job security. But so research funding is, I think, definitely one of the parts, but it's not the only thing.
Thank you. Let's take the audience questions.
Hello? Okay, yeah. So, first question probably written with the quantum computer. But we have the right persons here to decipher it, so because it ends abruptly. So, sorry?
Not enough symbols.
Okay, but I will read it as it is, so let them figure it out. So we have really, really smart guys here. So, questions that go in parallel. What other tech needs to be enhanced for QTech to have accelerated development? What tech needs to get cheaper for QTech to go
Cheaper, okay.
Yeah. So what tech would accelerate the development of quantum technologies?
What other technologies? Yes.
Yeah, quantum technologies, and as I think it was Roland who pointed out that there's actually a large variety of quantum technologies. Quantum computing is just one of them. And then what accelerates it, it also depends a bit what kind of quantum transistor you're using. We have different things which hold us back. So I am working with superconducting qubits, so small electrical circuits which go superconductive, and I could answer for them, and maybe Roland answer for trapped ions.
Yeah.
So today the state of the art, or like something to be proud of, is around 100 physical quantum bits. And the next stage is about 1,000, and for this 1,000, one of the technical things which is necessary, which to scale to that level, is ability to combine multiple different chips together into one working device, like chiplet technology, and how to do that without destroying the properties of these sensitive qubits on it. Like they have to be super clean, and how to assemble them such that they wouldn't get dirty. How to put them all into one big box which wouldn't have a self-resonance frequency which is at the same frequency. So this is one of, like, these sort of things are something which is being worked on, or like there's a similar previous generation. What they needed like a small holes through pieces of silicon which you fill with metal. So they are called vias in printed circuit boards, like how to connect the different layers of conductors together. And we need superconducting vias. So how to deposit aluminum into small holes such that they would be superconducting if you cool them down, so there would be no oxygen inside and so on. So it's material science.
Roland, what do you say? What would have to be happen to make it cheaper?
So big challenges are in technology integration, at least on our side. The building blocks all exist. We have solid-state lasers, we have microwave electronics, we have chips and CMOS foundries. We want to bring them together. There's already a massive revolution going on, and people can join this in building visible photonics. So integrated photonics where you deliver visible light. Integrating photonics with electronics, making packaged devices which are robust, miniaturized, is something which is always useful everywhere. All technologies require packaging of different technologies, integrating different technologies. So I know it's pretty broad, but definitely the field is in a place where the building blocks are there. Integrating them fast and prototyping fast is something where one can always improve. There's lots of
Joosep, you are a software guy, so what's missing? Do we need better hardware in order to do some jumps in
So
software?
I don't develop the technology. I can't speak what would be useful to make that faster, but to make it more sticky, I think would be useful. Like if there was some use case that's actually you really want to use it, that's economically viable, that's maybe you know, ChatGPT is like fun to use, right, for everybody basically. So if there was something like this, I think this could accelerate a lot, but this is just sci-fi right now.
A killer app which would keep
Killer
the
app,
lights
exactly.
on, which would guarantee funding, give job security, which would also accelerate. It would give us more confidence.
Game in quantum computing.
Yeah, we need a Doom on quantum.
Doom on quantum computing.
But this will
maybe
never
not a
exist.
Doom, but a super algorithm that,
Yeah.
with a very small number of faulty qubits, gives you crazy advantage.
Yeah.
Would be amazing.
This was awesome. I really like the lottery ticket metaphor. I got better understanding where we are now and where are the awesome opportunities and what we should do in Estonia. Thank you very much for Quantum Estonians.
Right. Thank you, Kalev. Thank you. Thank you.